team at SingleStore.com. So let me introduce our speakers today. We have Sukh Sundar. He's the VP of International Pre-Sales at SingleStore. And we also have Jitendra Ranjan, Senior Enterprise Solutions Engineer here at SingleStore. Welcome, Sukh and Jitendra. You now have the floor.
That's great. Thank you so much, Diogo, for the introduction. And I'm absolutely delighted today to be partnering with Jitendra on my team. I'm running shotgun on this, and Jitendra has been working very diligently preparing for this webinar. We've actually got some fantastic content to go through. We're with pre-sales, as you'd expect, we're not just kind of talking through some slides. We've actually got some real detailed analysis that we're going to do on this workshop. So it's more of a workshop than a slide presentation. And I promise you, there's a lot of detail here, and I'm sure if you stay with us, you're going to learn a lot. And even I, having been through this a number of times, even I learned a significant amount from the details that Jitendra has and will go through today. So let me just kick this off with an introduction. As Diogo said, my name is Sukh Sundar. I'm fortunate because I get to see many different customers, many different projects across many different verticals, and a vast region that my team and I cover. Many of those engagements that we have are all about migration, are all about either augmenting what's already there or replacing some of the legacy data landscape and consolidating it onto SingleStore. But before I go on and talk a bit more about some of the detail we're going to cover today, I'd like Jitendra, you to just introduce yourself as
well. Thank you, Diogo and Sukh. So hello everyone. I'm really appreciate you all for attending this webinar today. Let me introduce myself. My name is Jitendra. I'm a POC factory team lead. Being a POC lead, my job is to find acceptance of our solutions among end users. I'm based in Bangalore, India. So that's a brief about me. We have a lot to cover today, so we really should begin. Yeah.
Thank you, Jitendra. And you're right, we have got a lot to cover. So I thought I'd put this up just so you know what we're going to cover. So as I said, we're going to go into the details in this workshop. We're going to show how to identify kind of hot, warm, and cold data, looking at kind of legacy systems like MySQL. This continues on a consistent message we've been talking about for some time. We're not just going to talk about it, but as I said, we're going to show some scripts which allow you to investigate and identify what kind of data falls into each of these categories. We're going to show you how to do that. We're also going to show you what the results of any kind of migration will be. Jitendra is going to go into the detail about identifying not just the benefits, but also the performance gains that you can have. And we'll do this with some focus on MySQL. Why do you want to do this? How do you do this? And where to start. So we've got a really good lineup of topics to cover. The first topic I'm going to cover is around the temperature of data, and then Jitendra and I will do a bit of a double team, a partner act on some of the other topics that we will cover. So it is a long workshop, but it's a deliberate long workshop, so you get to see and hear about all the details that we're going to cover around this migration. In saying that, there are different ways of adopting SingleStore. We summarize those strategies into these kind of broad buckets of build, augment, and migrate. And there's no clear you must do augment, you must do migrate, you must do build. It really depends on the use case, really depends on your circumstances. In many circumstances, we will replace completely the legacy data architecture, and that legacy data architecture, as I said, might be kind of MySQL, could be MariaDB, could be any number of different databases, data warehouses, kind of big data style of architectures. The area we're going to look at today is more around augment. This is where you have a specific data architecture in place already. You identify particular types of data types. This is the hot data type, and we migrate that hot data type into SingleStore. But then you're adding augmenting to the data landscape by providing this kind of SingleStore acceleration layer. The cleanest, obviously, is the build. That's a greenfield opportunity that you have, a greenfield net new application build. But our focus is going to be around the augmentation strategy. When do you want to migrate? When would you migrate as an architect? You can almost identify the augmentation strategy by looking at these key kind of areas. The first is when concurrency starts to become a drain on the system, when it has an impact, you can't respond to the applications, the data hungry applications or the analytics in time. The experience is degrading as you start to scale, and the number of people that want to use these applications is growing. The data ingest demands are increasing. The rate and speed and velocity and variety of that data that's been imported into the application, into the database, is increasing. There becomes high availability becomes a priority, where the application becomes a core, vital, critical asset in the organization. Therefore, it cannot go down. It has to stay up. It has to be highly available. You need to, there's OLAP data sets, and the demands of slicing and dicing large amounts of data become a key requirement. You want to process real-time data whilst running the OLAP kind of slicing and dicing of queries. You want to maintain large sets of data without kind of impacting the transactional import of that data. And I think the final thing is, the demands, obviously, from different teams, either from the data science team or other areas of the business. But the final thing for me is that latency, that where the latency increases to such a point that it absolutely kills the customer's experience. So these are the reasons why you'd look to augment and why you'd look to kind of migrate over to something like SingleStore. So let's jump into the temperature of data. How do we define hot, warm, and cold buckets of data? This is not, it's well known, maybe not a surprise to most people. And as I said, the architecture that we have in place at SingleStore actually covers everything that you're seeing here. It just so happens that right now we're focusing on a particular use case, which is around migration of hot data. But actually, the architecture has been built to provide actually all three types of data and is available to put into SingleStore. So what is the characteristics of hot data? That's the frequently accessed data, requires kind of premium storage, SSD, to make it available at high speed, consumed by kind of OLTP style of workload, but supports kind of high concurrency access, high concurrency load of data. Warm data is less frequently accessed, requires slightly slower storage, more kind of SSD than in memory. Hot data is typically in memory. Warm data is kind of typically SSD. Consumed by this kind of combined OLTP OLAP style of workload. Less concurrency characteristics than the hot data, the in-memory kind of data that's identified as hot. And then this cold data. This is the data that you rarely access. You only want to access on demand. Requires a slower storage. In SingleStore, that would be object storage. You can push massive amounts of data. Terabytes, petabytes of data can be stored in object storage now in the latest versions of SingleStore. A lot less concurrency is required for accessing this data. So these are the kind of hot, warm, and cold types of data that have been identified, and some of these characteristics kind of move around. But we in SingleStore look at hot data as in memory, warm data as kind of SSD, and then cold data into something like object storage. There are, if we look at the different ways in which you can identify this from legacy systems, there's different techniques. You've got to be careful with some of these techniques. A bit of a warning before you start turning on some of the logging that we're going to talk about here. You've got to be careful, because turning on logging can consume large amounts of disk, large amounts of data can be deposited to these log files. So once you've run them, you've got enough data to go and do the analysis. Always kind of go back and disable whatever you've done. Otherwise, you start to generate a lot of data which you typically will and don't need. The technique that we're going to look at is turning on a lot of the logging and posting those to the general log. The general log is what gives you access. It's the single kind of source of access for all of the different types of commands that are being run. You can have a look at the DDL. You can have a look at the different operations that are being executed. But what we're going to do is actually filter that log file, and that's what we're going to do in terms of looking for the different inserts, the different updates, different delete statements that are happening, and to what extent are those happening within the legacy database. So as I said, there's kind of many different sources. You could have a look at the binary log, the query log, the data dictionary. There's different ways in which you can do it. We are going to have a look at the general log, which is the source we're going to use, and then we're going to figure out what is hot data based on the information that's gathered within that general log. So with that, I'm going to switch to showing you how we do this. That's great. I hope you can see this now. So as I go through this, so as you can see, we've got a script here. What we're doing is on the left-hand side, I'd like you just to have a look at this script. We're going through the general log. Actually, what's really interesting are the last three kind of grep statements that we've got in this script. The grep statements are what are looking for the different inserts, which tables are using those inserts, and then identifying and collating the numbers around how many inserts have been done, how many selects have been done, how many updates have been done, and which tables those are being done on. So let me execute the script. That script is what's doing the grepping through the log. And what you'll see, what I'll start to do on the right-hand side is start to update you with the information that we're getting. So as you can see, the output of the script, the output of those grep statements that we've done, is you can see some of the inserts, some of the selects, some of the updates that have been identified. You can see in the far left-hand column the number of times those commands are being executed and which tables those are being executed on. On the right-hand side, what I've got, if you can see on the right-hand side, is the hot, warm, and cold identifiers, and you'll see that I'll start to identify some of the particular tables that are being absolutely hit and hammered by the legacy system. So you can see one here, one of the tables, which is order history. There's not a lot of activity. There is some selects going on that, but it's not heavily hit in other areas in terms of inserts or updates. I continue to have a look. This is an interesting table, which is orders. You can see the number of inserts that are going on in the order table. And then I can go and have a look elsewhere. You can see the selects on the order table as well. So there's a combination of SQL going on here. And you can see further down, we've got some updates there as well. So that is a good candidate, which is doing inserts, selects, and updates, and at some volumes. So we've identified that as hot data. So it's a great, you can see what we're doing here. Then again, we have a look at these kind of big inserts coming in from the login table. You can see we've got some updates going on there as well. So again, it's a great identification. We have a look elsewhere. We can see the login table is also doing some selects as well. So again, it's fantastic. It's a good candidate, like we said in the identification, a good candidate for kind of identification of hot data. And you can see now there are some kind of, we've identified some warm data we would have as well. If you have a look at the table we've got here, you can see we're looking for different selects, different inserts, and you can see the compliant table is not just doing inserts, it's doing some selects, and then you can see some updates as well. And there are significant volumes, not huge, as you can see there, but it's another great candidate for not hot data, but warm data. So hopefully this is just by a very simple script. You can see the turning on of all of the logging on the legacy system. It was a MySQL database that we did this on. Using that simple script that's been created, grepping through all of the details gives you this really kind of simple identification output to go and have a look at and identify the different types of hot, warm, and cold data. The significance here being in the exercise that we're going to do and the migration that Jitendra is going to do next is on the hot data. So we're going to update the tables and migrate the orders table into SingleStore. And with that, I'm going to switch back. So, how and why would you want to augment? Having identified the hot data, why would you want to do this, and how would you do it? So augmenting with SingleStore, the great thing here is we are wire compatible with MySQL, so you can transition your data and your applications from MySQL to SingleStore database, which is pretty straightforward. All of the data types are fully compatible and fully supported. This does mean that you have this kind of acceleration layer. I deliberately use that word acceleration layer because we're augmenting, we're not completely replacing in this exercise. It gives you like this kind of two-tier architecture, which enables you to kind of independently scale an aspect of the application, and all of the queries, all of the operations can be focused on this kind of acceleration layer, and you can dynamically update without having to restart the node and make that node highly available. So why are you doing this? You get all of the benefits of a new kind of highly distributed relational database, um, uh, but having maintained all of the SQL compliance that you would have without having to go through a redevelopment, a new kind of a new data model, which you'd have to do with other kind of NoSQL style of databases. With that, I'd like to hand over to Jitendra to start talking about the bottlenecks and what are the impacts of those bottlenecks. Jitendra, do you want to go through this before you jump into your long work of going through this and showing this and how it actually works?
Yeah, thanks, Suki. So now we are going to discuss on the bottlenecks. Suki, can we, so that slide bottlenecks?
So let's see whether after the delete of these records, the space is returned to the operating system or not. So it may take some time. So let's wait for that. The current size of this table is 1.7 gigabyte. Yeah. So the records are deleted from this table. So let's see the size first of this table. Surprising, your records are deleted from this table, but the size is still same. Let's see if there are any records in these tables. So I want to show you the records available in this table. Price, 0 records, but space occupied by this table is 1.7 GB. So for this, you will have to go through the manual process. You will have to optimize the table, and then you will be able to reclaim the space. So just imagine if you have a large table and optimization is not possible every time. And for your information, optimization has some overheads. So optimization, when the optimize is running, your transactions are blocked. So just imagine if you have a transactional table and you'll have to do these activities frequently. So it's a big problem for this kind of engine and opting. So now if you see optimize is run, now when you see the table, now you can see the space is returned to operating system. Now it is 96K. So this is the big problem. Now coming to the second bottlenecks. So inefficient buffer pool design. So let's suppose you have a buffer pool of 128 128 MB. So let's see what is the current size of the buffer pool here. Yeah, so it is roughly 128 MB. So let's suppose what are these? What are the queries results? Data and index data is there in buffer pool. So there are nothing. There are few bytes of memory occupied by this buffer pool. Okay. So imagine that you have a few queries in that table. Let's suppose I'm running one query. Let's start from, we could say, ecom dot login. This is some thousands of records. Let's see after this. Let's see what are the stuff in buffer pool. Now you can see, the login table has occupied this much of byte. I can say this much of byte is consumed by this query in buffer pool. Now let's suppose I have, okay. Now when you run any select statement without wait clause, when you load any data to that table, if there is no memory in your operating system for this buffer pool, it is occupied by this where clause query, which has no where clause. Let's see. Let's load one data, one table. So while it is running, let's discuss on that third bottleneck. The third bottleneck is memory engine, which is used in memory data storage. But when your MySQL server restarts, the data flushed from that table, that actually leads to your data loss. So we'll see that the third bottleneck also practically. So let this let this command run, and then we can see how the buffer pool design is inefficient for your large queries. So when you run any SQL statement without where clause, or when you run load command for the large table, all the memory used in that buffer pool is occupied by this statement. So the other queries are automatically invalidated, and it will have to return the record from disk, not from memory. So this will hamper your other queries time. So let's cancel this. It is let's run. So now let's see what is the buffer full condition now. Okay, just imagine all your queries which you run on the login table is invalidated automatically, and others also. So now you have only records or indexes data for this table only. So just imagine if you have a numbers of queries running in your database, which is actually satisfied by this buffer pool. When it is invalidated, just imagine how much pressure will be on disk. So just this, for this bottleneck, I wanted to show you this practical. Okay, so this is not good for your hot data to maintain. This kind of buffer pool is dangerous for your data, especially for hot data. Now coming to that third bottleneck, so memory engine. So memory engine, which is used as in-memory data storage by MySQL, but when your server restarts, data flushed from your table, which actually leads to your data loss. So just imagine how inefficient MySQL memory engine. Let's see that. So I'm creating, I have already created one database, table. Let's see the structure of this table. So this table is memory. This table has a memory engine. Okay. Now let's now see. I am inserting just 1,000 records in this memory engine table from the table which has we just loaded in that table, simple insert. Okay. Now, if you see, thousand records are there, and let's restart. I'm going to restart my MySQL server. Then we will see whether records are there in that memory table or not. You will see that records are flushed from this table, which is very, very dangerous for your queries, uh, which you are actually written to handle your hot data. Let's restart this server. Then we can see the records are there in memory or not. So while it is running, let's discuss on the fourth bottleneck. The fourth one is a manual recovery of slave machines, which is claimed to be used in high availability. So, we use a number of slaves, application slave in MySQL, which is used in high availability. In many slave, fail situations, DBA has to intervene and recover it manually. So, if you see, there are lots of situations where DBA has to go to slave machines and slave and master machines and handle these failure situations by doing some activities on both the systems. So this is not, I can say, this is not automatically managed by the replication ecosystem. So we'll see that the fourth bottlenecks also. So let's see whether that third bottleneck is, we are going to see that third bottleneck. So we have just restarted MySQL. Let's see now. The records are there in that. No, it is gone. Surprisingly, there is no record in that table, which was actually run on memory engine. So this is very inefficient design for your queries, which are you have written to handle your hot data. Now coming to that fourth bottlenecks. So for this, let's see. I have one replication slave, which is you can see up and running.
So we were talking about bottleneck, so number 4 for data in MySQL. So MySQL slave is claimed to use for high availability, but this is not at all suitable for hot or transactional data. Data syncing are far behind between master and slave for large transactions. To prove this, I have installed MySQL master and slave on two EC2 machines in same zone. Same zone, we kept that same zone just because, save the latency. I'm running one simple insert script on master, and at the end you will find that applications are not getting results. It somehow leads to business loss. So this is my slave machine, and this is my master. There is one is insert script is already running. If you want to see, this is my insert script. We have three tables: login, orders, and complaint. In all these three tables, I am running iteration of 1 lakh, 1 lakh, and 1 lakh for all the three tables. Insert commands only. So one script is already running here, and
Let's see. So, what is the current status of slave? Is this it's not currently behind? So, we'll keep you know you will find all the records here in master and slave for all these three tables. So now let's see if I run one more batch of this insert script. Let's see what happens. Yeah, started. So after some time, you will see that there, your slave is far behind from the master. So that means the master and slaves are not in sync. So whatever you are inserting on the master, you will not get the same result, same count on the slave server. So just imagine you have a transaction system and you want up-to-date results on the slave as well. So you will not find, and this will leads to your business loss. So let's see that. So currently there is no behind. My two scripts are running now. So I have run one more command to load the data in a simple insert table. So I have three load is running, two through insert script and one through that load command. So let's see now what is the slave status now. It is up and running, no behind. Let this load run. Then we will see the count of the tables, both sides, master and the slave. Then you will find whether your master and slave in, is in sync or not. This is just a very few no transactions, few inserts and loads. So it is inserted now. Now let's see. Select count one this table on the master side, and let's run the same command on the slave side. Let's see now. This is 34142T077 is my master, and 18.117.188.75 is my slave. See, what is the here on the master side you are finding this much record, and on the slave side you will find this much zero records. So see how dangerous this slave MySQL slave system for your for data transactions. So I would not recommend to go for MySQL for hot data. So consider the SingleStore. You will find always a sync up between master and slave. See now, this is behind. Just a few transactions. I'm running only three scripts. One is already completed, and two is only two are running. So in this load only, it is behind now, and you will find there's a huge gap between this table as we see earlier. Yeah, the records and this much record on the master. So now we are going to discuss on MySQL or data bottlenecks number 5. So in this topic, we will discuss MySQL archive engine. So MySQL archive engine is claimed to be a suitable database engine to store historical data, but this engine lacks lots of basic features of the database. It does not support delete or update operations. It does not support partitioning. It does not support multi-versioning concurrency control. It does not support clustered and hash indexes. It does not support data cache. So imagine if you have, if you are maintaining one large historical data set in a archive engine, MySQL archive engine, and somehow you uh, have a requirement to delete or update few of the records, and if you are not able to do that, just imagine the situation how you will deal with those operations. So in this demo, we will see how this archive engine behaves with those operations. Let's see. So for this, I'm going to create one uh, archive engine table. And I'll put some record in this table. Records are being inserted into simple insert archive table. So let this insert be completed, then we can see these delete, update, and other operations are allowed or not. These are some basic features of a database. If it is not allowed, then imagine how you'll maintain your historical data from your hot data set to historical data. How will maintain that? So it's just I want to show you. So the insert is completed on archive engine table, and now I want to update some records. Let's see. Yes. So table storage engine, this archive engine table is not doesn't have this option to update. This is very basic features. Now I'm going to in delete few records. Let's see. Delete is also not supported. Now let's see to add one index. So index is very basic to fasten your search operations. So this is very basic feature of database. So let's create an index on this table. So this is not supported. So this you can see these very basic features are not supported on archive engine table. This is archive engine, which is claimed to be a historical to maintain the historical data set in these engines. So this was bottlenecks number 5. So now we will see the bottlenecks number 6. So the 6 bottlenecks is related to a MySM storage engine. So MySM storage engine is designed to support fast rate. It does not support auto crash recovery, and as a result, it may take minutes and hours to repair it manually, which may lead to application failure. So if you are maintaining a record set just for search operations, if you have an application which requires only search operations, and you are maintaining on that MySM table, and if somehow sometime your server restarts or anything occurs due to hardware failure or something, so this MySM table will be crashed, and you will not be able to repair it automatically. So you'll have to go through a manual process to repair it. So let's see how it works. I am going to create. I have actually one. If you can see, I have one MySM table. I want to show you one MySM table. So this is MySM table. I am going to insert. Let's see first how many records in that source table. So what we will do, we will try to insert in that MySM table, and while inserting, we will stop the EC2 instance, and we will see the status of this MySM table. So let me do some more, insert some more records in this. Then we will insert from this source to the destination MySM engine table. Some value into that MySM engine table from a source table. And while insertion, I will shut down the server, and let's see the recovery of this table happens automatically or not. Insertion started. I'm going to shut down the server to see the. You can see this is the same server 3142.2007. I'm going to shut down the server. This is the same server. Let me stop the instance. Got it. Stopping now. Now the connection is closed. Let this up. Let this stopped. Okay. Press it. It is stopped now. Now I'll restart it. Start this instance. And after starting this, I will go to that MySQL server and see the status of that table, whether the table is in good condition or it is crashed. and we'll show you how to repair it manually. So this is a no again a manual process. So I'll not suggest to maintain your fast search kind of table in the MySM. Rather, you should consider single store mm, col columnar table. That is column store table. Search is fast in that single store column store table, and good compression you will get, and there is no crash kind of scenario in that table. So we'll always get a good result from single store column store table. Let's see now. So my table was my SM table. Let's see. See now, the table is crashed. So this is how the MySim engine table is not suitable for any kind of search operations. So anytime you, when your server is restarted, the table may crash. So all the search operations may fail. So this is not at all suitable for your all data.
Thanks, Jitendra. I'm just going to bring up the slides again. Actually, because we've gone through a lot, it might be a good idea just to summarize some of the bottlenecks that you've gone through, Jitendra, first, before we move on to then show a bit about the migration.
Yeah. So can we show that slide, migration slide? Now we are going to discuss how do we migrate data from your MySQL. I'm not talking about only MySQL, any legacy database system to single store. So let's see that how we can migrate from MySQL or any legacy database system to single store.
Now, as you know, the importance of hot data, methods of identifying hot data, and also know when and why to migrate MySQL hot data to single store. So now let's discuss the ways to migrate hot data to single store. On high level, there are two methods of migrating MySQL hot data to single store. The first method is manual, and the second one is automated. So in manual process, you have to take the DDL of MySQL tables. So identify the components of MySQL DDL and change to S2 compatibility, like data types, what are the indexes, what are the functions and table types. Restore after changing those components, restore that ADL to your single store, and then after restore the data to single store. And in last, you can change the queries, SQL statements, and do the functional testing. This is the just a manual process. So in automated process, you to migrate a data and the DDL, you just have to use one tool, that is a single store replicate tool. And that single store replicate tool works in two modes, snapshot and CDC. In snapshot mode, you'll move all the DDL and data in one shot. And in CDC mode, you can migrate your data incrementally. So, and after this process, you just have to do the functional testing of your queries. So in this demo, I'm going to show you the automated process through which you can replicate your MySQL or data to SingleStore. So you can see I have installed a MySQL replicate tool in my MySQL server machine. You can see also there are three major component of this replicate tool. First one is I can see the source YAML file. The second one is destination YAML file, and the third one is filter. So in source YAML file, you will mention the source database informations, the database IP, the username, the password, and the database and information, all the database information. In destination file, you'll mention the IP of destination SingleStore server, the user, and the password. And in filter, what are the database you want to migrate, the table names, and so views, table names. If you don't want to mention the table names, so it will migrate entire database which you mentioned in that filtered YAML file. So let's start and run this replicate tool and see how soon it migrate your data from MySQL to SingleStore. The replicate is started. So let's see how much table it is going to start. There are 4 tables: orders, logins, orders history, and complaints. And so see the number of rows it is going to migrate, and see how soon it can migrate all your DDL and the data to your destination SingleStore server from MySQL. So here is the MySQL and here is the SingleStore. So see, in very few seconds, it migrated all the DDL and the data to SingleStore from your MySQL database server.
Thank you again, Jitendra. I'm going to go back to the slides. I think we've covered the migrating of the hot data that you identified, some of the tables. Shall we go on and talk about some of the performance gains that that have come about as a result of the migration? So I'm happy for you to kind of share some of that detail if you're happy to do that, please.
As you saw, we already identified the hot data and migrated to SingleStore. Now let's see the comparison chart of performance on very basic insert, update, and select commands. And this is by both databases on table having 4 columns, just one table. At the end of the demo, we will find that how hot data struggles in MySQL, and it leads to impact your business decisions. Let's run a simple script having insert, update, and select statement on both MySQL and SingleStore. We will also run data dictionary SQL commands to compare disk utilization by a table. So let's run a script. So just for your information, I have a left pane and right pane. So in left pane, I have a MySQL command line, and in right pane, I have a SingleStore command line. So let's run a script and see how many inserts, updates, and selects are running. So this is MySQL performance script. Let this run first, and this is I'm going to run SingleStore performance script. Oh, see, the SingleStore performance script has run. The SingleStore took 1 second for running 10,000 statements, insert statements. To run 1000 update statement, it took only 4 seconds. And to run 14,000 select statement, it just took 7 seconds only. But in the other hand, if you see, MySQL script is still running. Let's see how much time it is taking to complete this script statement having insert, update, and select. Now see the difference. The 10K insert statements on MySQL took 99 seconds. In SingleStore, it took 1 second. 1000 MySQL update statements took 101 seconds, and SingleStore took 4 seconds only. 14,000 MySQL select statements took 71 seconds, and SingleStore took only 7 seconds. Now see the difference. What a huge difference between MySQL and SingleStore. So let's quickly check the records in all these tables. I'm going to check first in MySQL. Let's quickly check the first table, like complaint, select, and let's check the same table in SingleStore. It is more than MySQL database. Let's see the second table. See the difference in SingleStore. For that table also, it has much record as compared to MySQL. Let's see the third table. In orders or table also, SingleStore has much record than MySQL. And see the last table. Now see the difference in SingleStore for order history table also. SingleStore has much record as compared to MySQL. So the difference even on larger data size on SingleStore, it is taking lesser time as compared to MySQL. See the difference. So these are, let's see the comparison once again. Here is MySQL site, and here is I can show you SingleStore side. There is no comparison. So how fast it is the SingleStore, you can realize. Now see the disk comparison, for the order table, uh, how much time or how much this size order table took on MySQL, and how much this size SingleStore took on SingleStore size. So let's see. I'm checking first the MySQL. See, the order table is taking 134 MB, and let's see on the SingleStore. In SingleStore, the order table took only 19 MB. So see the difference of disk utilization also. It's a huge difference between MySQL and SingleStore. So now I hope you now realize that moving to SingleStore will be your right decision. You can put all your hot data into SingleStore and gain super fast performance and save lots of disk spaces too. Now let's see the final comparison chart. So you can see both in terms of performance and disk utilization. So this is the final comparison chart. So there's huge difference between SingleStore and MySQL performance, both all in terms of inserts, updates, and selects. So it took only 1 second. It took 90 seconds. Update took 4 seconds. MySQL took 101 seconds, and select took 7 seconds, and MySQL took 71 seconds. These all are in batch mode. So disk utilization also, SingleStore took 19 MB only, and disk and MySQL took huge 134 MB. So that's the huge difference.
Thank you again for the comparison, for the movements, and for all of the hard work, Jitendra, you've done. I'm going to finish off. Going to kind of shift gears and finish off the presentation. Just talking a little bit about, why people are doing this. What is the reason? The three main reasons, common reasons why we see people wanting to use and migrate and jump into SingleStore around. You can see from the example, just the basic examples that Jitendra's given, the speed, the scalability, the scale out options, but also the SQL compliance that we have in terms of this kind of new SQL highly distributed relational database structure that we've put in place. Those are the three S's, three reasons why most people will want to jump into augmenting what they've done with SingleStore. There's some really interesting aspects, obviously, to the SingleStore platform and architecture. One of the biggest that I see in this combined database, this unified database, are the data types that you can store inside of SingleStore. So you can combine JSON structured, semi-structured data, geospatial data, time series data. You can store that in terms of a relational model, and then run full text SQL search over all of those different kind of data types, which is significant when you're trying to collapse and combine different kind of databases into a single database. But also, obviously, the augmentation of some of the legacy database infrastructure that you already have in place, and Jitendra's talked about and proved and shown the MySQL augmentation today. Continuing on, we've spoken about how SingleStore is this unified database for data-hungry applications, for fast analytics on any data. Anyway, we've got a significant number of customers that are working with us, and we're adding value to their business. We do have this concept from dual store to single store. This is the kind of movement that we've got, and this combining of this concept called universal storage. This is kind of a single data type. That data, single table type, forgive me. That single data type gives you everything you need to run that table in memory, in row store or column store. So we have this kind of concept of dual store, universal storage, which provides you this kind of simplified architecture. You don't have to design around this. You can do in database ETLs, transformations. It significantly collapses the multi-tiered architecture that people are used to. Significant a collapse in terms of the number of different products into a single architecture, which means there's kind of less teams, less overhead, lower costs in terms of a single architecture, and obviously some of the lower latencies that comes with. So I'd like to kind of finish off. I'd like to thank everybody for joining us. I know it's been a long workshop, but I think in terms of the value and in terms of the information and data that we've added around identifying of the different kind of temperatures of data, hot, warm, cold, how to look for those kind of different data temperatures, how to move those identified data types, what are the consequences of moving hot data into SingleStore, and what are the benefits of doing that. And with that, I'm going to hand back over to Diogo to finish off the webinar that we've had today. But thank you so much, everybody, for staying and joining us and walking through this detailed webinar workshop for us.
Thank you, Suki. So thank you, everybody, for participating today. Thank you, Jitendra and Suki. We will send you a follow-up email with today's recording and a link to our managed service free trial. We are offering each user $500 in credit, so you can start a full workload today. And lastly, check out our other virtual events at singlestore.com/events. Thank you for joining us and have a great rest of the day.